This is Engineering 246, Lecture 2, Part 2. We're going to finish up Chapter 2, and for this part, we're going to start talking about something known as Poisson's ratio. So Poisson's ratio comes about from when we stretch on a part in the axial direction and observe what happens in the lateral, or the directions that are perpendicular to that axial direction. And pretty much everybody can imagine that when you stretch on a long rod, it elongates in the direction of stretch, but then it shrinks in the directions that are perpendicular to that. Okay? And those are what we call the lateral directions. And again, just like a lot of things in mechanics of materials, a lot of experiments have been performed, and that's where a lot of these equations are coming from. A lot of these equations, these properties, these definitions come about from pure observation. So in the case of this shrinkage in the lateral direction, what people have found is that the amount of shrinkage, or it could also be an amount of expansion if you were to compress your part in the axial direction. So the amount of change in the dimensions of the lateral directions is also a material property. And this property is referred to as Poisson's ratio. So we have yet another Greek letter, okay, that you must memorize and get comfortable with. This is Greek letter nu, lowercase nu. It looks like a curved V, okay, but this is actually a Greek letter. Okay, this is Greek letter nu, and it's referred to as Poisson's ratio, named after a person, like a lot of these values, and sometimes it's just simply referred to as the Poisson ratio. And its definition is very simply the ratio of the strain in the lateral direction to the strain in the axial direction. So there it is. Okay? And what you'll notice is that there are absolute value signs around this definition. And in this example, the x direction is our axial direction. So we are pulling in the x direction and then measuring what happens in the y and the z directions. So the reason that we put in these absolute value signs is because without the absolute value sign, if you were to stretch the part in the x direction, your axial strain would be positive, and then because it contracts in the y and z directions, the strains in the y and z directions will be negative. And that ends up giving you a negative value for Poisson's ratio, which is fine, but a lot of times we don't like having negative quantities for a material property. Right? A material property is something that you want to be easy to tabulate, you want to be able to work with very easily, and usually that means keeping it positive. So therefore, we convert it into a positive value by either taking the absolute value, or then we take the negative of that ratio. So Poisson's ratio means basically the ratio in the deformations. And if you think more about this, okay, there has to be lower and upper limits for your Poisson's ratio. Okay? It's a material property, as I said, and I'll talk more about why it actually is not found in a lot of materials properties tables. Okay? But we'll get to that in a moment. All right. So what are typical quantities for this property? For most of the metals that we're going to be looking at, something between 0.25 and 0.35 is typical, okay, as you see down here. the maximum allowable value is 0.5. 0.5 is what we refer to as an incompressible material. Okay, it is the absolute largest value that you could have for Poisson's ratio. And things like rubber, natural rubber, approach that limit. And then at the lower limit, of course, you really can't get 0, but you might have materials that get close to 0. Right? And something that's close to 0 basically means you stretch on it in one direction and it barely changes dimension in the other directions. Whereas in the case of rubber, you can imagine what that means. Right? You stretch on it in one direction and then it shrinks by half the amount of stretch in the other directions. All right, so that's Poisson's ratio. And it's definitely something that you can see, right? You could take, roll up a piece of clay, pull on it, stretch on it, and what you can see is that it thins out. It gets long and thin, right? That's Poisson's ratio at work. All right, now, Poisson's ratio is very easy to observe, right? And we all kind of can get a feel for it if all you're doing is applying a force along one axis, right? If you're only stretching in the x direction or the y or the z directions. But what happens if you have something like a cube, like we're showing here, and then you stretch that cube or compress it in all 3 axis directions? Now it's very hard to imagine what's going to happen, because if you take a look at this, when you stretch it in the x direction, it wants to shrink in the y and z directions. Yet, we're also trying to directly stretch it in the y direction, which is going to try to cause it to shrink in the x and z directions. And then finally, we're stretching it in the z direction in this figure, which means it's trying to contract in the x and y directions. So how do we get a feel for how much the actual dimensions are going to change in a case like this, where you're applying forces in all 3 directions? If you think back to the first part of this week's lecture, we talked a lot about superpositioning, and I had mentioned that in superpositioning, you basically look at all the different types of forces on an individual basis. And then you look at the effect of each of those types of forces and you add up all the effects together at the very end. We're going to apply superpositioning in this case as well, except that we don't look at types of forces. We're going to look at the individual stresses, meaning we're going to look at sigma x and look at what effect it has. Then we look at sigma y, then look at sigma z, and then we add up the effects of all 3 stresses to get the net effect. So the end result of doing this is something that we call the generalized Hooke's law. Okay? And the generalized Hooke's law is based on Hooke's law, but Hooke's law really applies when you apply just forces in one direction. Right? If you apply forces in all 3 directions, you need to apply Hooke's law to all 3 of those directions. So in this generalized type of loading, okay, what we're going to do is look at the strains. So if you think back to our definition for stress and strain and Hooke's law and all those definitions, what you have is sigma is equal to E epsilon, right? That's Hooke's law. Now, instead of looking at stresses, what we want to do is look at strains. So if solving for strain, we get epsilon is equal to sigma over E. Okay, and keeping that in mind, we're now going to apply superpositioning. Okay, so the way we're going to do this is this. When I apply stresses in the x direction, if I look at just sigma x, okay, that means I'm going to put in these epsilon, these subscripts here. Okay? The strain in the x direction due to my stress in the x direction is that. Correct? And then we know that when you apply the stress in the x direction, what happens in the y and z direction are determined by Poisson's ratio. So we had Poisson's ratio is equal to negative of epsilon y over epsilon x, right? Or it's epsilon z negative over epsilon x. Okay? So if I solve for epsilon y and epsilon z, I get epsilon y is equal to negative nu epsilon x, and epsilon x is given above, so that's negative nu sigma x over e. Okay, then epsilon z is negative nu epsilon x, that's also negative nu sigma x over e. Okay, and let's just do the same thing for sigma y. Now we're going to look at the stresses in the y direction. So sigma y is equal to E epsilon y. And that means epsilon y is equal to sigma y over E. Poisson's ratio says nu is equal to negative epsilon x over epsilon y. It's also equal to negative of epsilon z over epsilon y, because y is now my axial direction. Correct? So I have epsilon y, and that means applying Poisson's ratio to epsilon x, I get epsilon x is negative nu epsilon y. That's negative nu sigma y over e. Likewise, epsilon z is equal to negative nu epsilon y, negative nu sigma y over e. Okay, and finally, if you look at the stresses and strains in the z direction, sigma z is equal to E epsilon z. Solving for epsilon z is equal to sigma z over E. Applying Poisson's ratio, nu is equal to negative epsilon x over epsilon z, or also equal to negative epsilon y over epsilon z. Okay? Now solving for epsilon sub x, it's negative nu sigma, nu epsilon z, and epsilon z is what's up above here, right? So that's going to be a negative nu sigma z over e, and finally epsilon y is equal to negative nu sigma z over e as well. All right, so I've got these three stresses that result in three separate strains, right, in x, y, and z. So if I want to find out what epsilon x is, okay, epsilon x from superpositioning is going to come about from this, right, from a stress in the x direction. It's going to come about from a stress in the y direction, and it's going to come about from a stress in the z direction. Likewise, if I try to find out what happens in the z direction, right, if I try to find epsilon z, I know that due to sigma x, I have that. Due to sigma y, I've got this. And then due to sigma z, I have this. Applying superpositioning means I add up the three strains in the x direction to get the total strain in the x direction. I add up the 3 strains in the y direction to get the total strain in the y direction, and then I add up the 3 strains in the z direction to get the strains in the z direction. Okay, and what you end up with is this. Okay, this is what we refer to as the generalized Hooke's law, and we just went through the derivation, but you might want to go through the derivation on your own to make sure you understand exactly where all these terms are coming from, right? So epsilon, if I apply sigma x directly, then I am going to get a direct epsilon x. But due to sigma x, right, I get these strains in the y and z directions due to Poisson's ratio. For sigma y, I get a direct effect on epsilon y, but then I get these indirect effects on epsilon x and z. And finally, for sigma z, I get a direct effect on epsilon z, but then I get these indirect effects on x and y. That is the generalized Hooke's law, and the way we're going to apply it, right, is basically in situations where you have multi-axial loading. What we mean by multi-axial loading is that we have loading in more than one axial direction, more than one coordinate direction. So let's take a look at an example. Okay, I'll come back to all of that. So here is the example out of the textbook. You have a plate, and within this plate, okay, you're going to already designate the x, y, and z directions. You're given some dimensions here. You're going to draw a circle on this plate with 2 diameters, AB and CD. AB happens to coincide with the x-axis, and CD happens to coincide with the z-axis. They also tell you that you're going to apply stresses in the x and the z directions equal to 12 ksi and 20 ksi respectively. They give you Young's modulus and Poisson's ratio. Poisson's ratio is 1/3 in this case. Okay? Find the change in the length of diameter AB, the length of diameter CD, find the change in the thickness of the plate, and then finally find the thickness and the volume of the plate. For part D, I'll come back to that. We'll get to that. I want to mention something else about that. Okay, but before we do that, let's solve A, B, and C. So this is obviously a case of multi-axial loading, right? You have sigma x and sigma z, and you don't have sigma y in this case, but in some problems you very well could have sigma y. So can everybody see that if I want to find the change in the length of diameter AB, that's basically finding the strain in the x direction, because AB happens to coincide with the x direction. Once I find the strain in the x direction, how do I find a change in the length of diameter AB? Well, diameter AB, I know its original length. Okay, they tell you that it's 9 inches. And then you know strain is change in length over the original length. Okay? So once I have the strain and the original length, then I can find a change in the length. Okay? Then the same thing for diameter CD, except that CD happens to coincide with strain in the z direction. Then finally, for change in the thickness of the plate, that's obviously strain in the y direction. So generalized Hooke's law, the generalized Hooke's law is going to apply for this problem. Okay, so what you do is, for the first part, you say you need to find the strain in the x direction. So in order to find the strain in the x direction, if you look at this, you need the stress in the x direction, the stress in the y, and the stress in the z. Okay? And since you have Young's modulus in all 3 terms, you notice that it's just pulled out here. But then there's the stress in the x direction, 0 for stress in y, and then nu, or Poisson's ratio, okay, is negative 1/3 times stress in the z direction. So if you work that out, there's your strain in the x direction. And you could do the same thing, right? You do something very similar to find strain in the y direction and then strain in the z direction. Once you have those three strains, you just apply definition of strain along with the original lengths to find the changes in the lengths. So here they are, right? Change in the length of AB is strain in the x direction times the original length of AB. And then the same thing, or something very similar, for change in the length of CD and change in the length of the thickness. The very last part of this asks for a change in the volume of the plate. Now, one thing you can do about finding the change in volume is you could take those three changes in the x, y, and z directions. I mean, basically, you could find the change in the length of the x direction, so that would be strain in x times 15 inches. Then you do strain in z times 15 inches, right? Then you take strain in y times that 3/4 inch thickness, and then you multiply the change in the three dimensions together to find the change in volume. And that would be fine, but except it requires a lot of calculation. The shortcut has to do with this. This is a very interesting property, and it's useful, okay, in situations like this. There's something that is defined as the dilatation, okay, lowercase e, and it's given as this. You simply take the sum of your three strains, epsilon x, epsilon y, and epsilon z. Okay? And what that dilatation happens to be is the change in volume per unit volume. That means if you take E and multiply by your original volume, you're going to get the change in the volume of your part. That makes it much easier. We had already found our three strains. Okay? Epsilon x, epsilon y, epsilon z. So what that means is we just need to take those three strains, add them together to get the dilatation, and then multiply by the original volume. That's 15 inches times 15 inches times 3/4 of an inch. And that will give us our change in volume. Okay, so that's a nice little shortcut for finding the change in volume. All right, let's go back to the generalized Hooke's law for a second. And I just want to discuss very briefly this idea about rubber being incompressible or having a Poisson's ratio of 0.5. Okay? So if we apply generalized Hooke's law to a material with Poisson's ratio of 0.5, look what happens. And if you remember, I said something like rubber that's incompressible, okay, basically it's the very limit, okay, of what can happen with the material when you apply multi-axial loading. In an incompressible material, okay, your volume never changes. It doesn't matter how much you strain your part. Okay, you take this cube, you apply stresses in all three directions. The volume never changes. It could deform, it could change shape. Okay, it could go from square to some kind of a rectangular box, but its volume never changes. So how do we show that? Well, if you take the generalized Hooke's law, okay, and you say that nu is 0.5, solve for dilatation when nu is 0.5. Okay, that means we add these three equations together where nu is 0.5. Take a look at the x terms, the sigma x terms. Okay, if nu is 0.5, I get sigma x over e minus 0.5 sigma x over e minus 0.5 sigma x over e. What do these three terms add up to? 0. Same thing for the sigma y terms. They add up to 0. The sigma z terms add up to 0. So your dilatation is equal to 0. And what is dilatation equal to? Change in volume over original volume. So what is delta V? It's 0. Your volume never changes when Poisson's ratio is 0.5, as you have in a piece of rubber. Okay, and what that means is if your Poisson's ratio is not 0.5 and you apply multi-axial loading, then you are going to get a change in volume. Okay, so that's just a little interesting aside for you. Let's erase all of this. So you might recall I said several minutes ago that Poisson's ratio, although it's a material property, a lot of times you can't find it in the materials properties table. And a big reason for that has to do with shear. Okay, that seems a little strange perhaps. Okay, but let's go and talk about shear first, and then we'll get into why you don't find Poisson's ratio in materials properties tables. All right, so we talked about normal stress and normal strain, right, and how they're related through Poisson's ratio for multi-axial loading. And last week we talked about shear stress, if you remember, right? That was tau, Greek letter tau. And then in the first part of this lecture, at the very beginning, I said that when you have a shear stress, what you look for is a change in right angles. So let's talk a little bit about shear stresses and then the corresponding strains that occur. Okay, so shear strain in 3D, right, it's these 6 terms, which we said reduces down to 3 unique values. So we already defined a normal strain, and a normal strain had units of length over length, right? So it was always inch per inch or foot per foot or meter per meter. It's dimensionless. And it actually works out quite well for Hooke's law, because then what that means is Young's modulus has the same units as stress. Okay, let me just make sure everybody sees that. So Hooke's law, the regular Hooke's law, tells us sigma is equal to E epsilon, right? Sigma had units of pressure, so either pascals or psi. Epsilon had no dimensions, no units. You know, a lot of times when people write strain, they will still write inch per inch or meter per meter or something like that. And the reason they do that is just so it's easy to tell that you're talking about strain, right? But technically, strain has no units. So what units does E have? It has to be pascals or psi. So when it comes to shear strain and shear stress, we have tau. Remember, tau is also a force per unit area, so it has the same units. Okay? We want to come up with some kind of quantity for shear strain that follows the same pattern as what happens when we have normal stresses and normal strains. So we want our shear strain to also have no units. So how do we do that? We said when we apply a shear stress, okay, right angles get deformed, or right angles no longer stay as right angles. They become acute or obtuse. Okay. So how do I define a change in angle that has no units? Well, it's very simple. If you measure your change in angle in terms of radians, right, then radians, you might all remember from geometry, radians are dimensionless. They're not like degrees. Okay? They actually do not have any dimension. So if we use radians as a measure of our shear strain, or what happens when we apply a shear stress, then we have the definition that we're looking for. So that's going to be our formal definition for our shear strain. Okay? It's just a change in angle when you apply your shear stresses. So I talked about this at the very beginning of the first part of this week's lecture, right? How when you apply these shear stresses, you get this change in angle. And if you measure that change in angle, okay, in terms of radians, then that can be defined as your shear strain. So here is your new Greek symbol. Okay, shear strain is simply the change in the right angle when you apply a shear stress. When you apply a shear stress to a square, you end up with a shear strain, which is just a change in the angle. And we're going to use Greek letter gamma. Okay, so shear strain Greek letter gamma okay, measured in radians. All right. So people have done experiments on shear stress and shear strain, just like they did for normal stresses and normal strains. I remember how we talked about how you pull on a part until it breaks. Then you look at the plot of stress versus strain. Well, people have done the same thing for shear stresses and strains. And you could imagine the type of experiment that's done. Right? Let me just give you a conceptual idea of what's done. So you could take a square block. I'm going to attach something, a very rigid plate, to the top face. I clamp the bottom face, okay? And then instead of pulling in tension or compression, I'm going to pull on this top plate horizontally. You can imagine what happens there, right? So I keep increasing that force. I take that force divided by the cross-sectional area. That's my shear stress. And then I just measure the change in angle. You could imagine, right? If you look from the side, if you look head on, you start off with a square, and then it starts to deform like that. From the figure you just saw, if you just measure this angle, there's your gamma. Okay? So you could take a plot of tau versus gamma. What kind of plot do you think you'll get if you keep increasing your shear stress? I think a lot of people can imagine what's going to happen here, right? If you plot tau versus gamma for something like steel, you get a linear portion, you get this dip, and then you get that. What does that look like to you? What does that remind you of? Right? It's very similar to your sigma versus epsilon plot. So it's nearly identical. Obviously, the values are going to be different, right? But the general trends are the same. This slope is what we call the shear modulus. Our book, okay, and a few other books refer to this as the modulus of rigidity. Okay. So, new symbol for you. Uppercase G. Okay, not a Greek letter. Uppercase G is your shear modulus. And that linear portion, the linear portion of your plot, is Hooke's law in shear. And Hooke's law in shear is simply tau is equal to G gamma. So G, right, your shear modulus or your modulus of rigidity is again a material property, and it's listed in your material properties tables. All right. So now let's get to why Poisson's ratio a lot of times it's not given in your material properties tables. Okay. This is beyond the scope of this course, but it can be proven in more advanced mechanics and materials courses that E, nu, and G are related by this equation here. Okay, your shear modulus is equal to your Young's modulus divided by the whole quantity, 2 times 1 plus Poisson's ratio. What that means is this. Since E and G are listed in your materials properties tables, a lot of them don't bother listing nu or Poisson's ratio because you could plug in your shear modulus and your Young's modulus into this equation and solve for Poisson's ratio. Okay? And that's pretty much the reason that Poisson's ratio is not given in a lot of tables. Okay? They figure you could go and solve for it yourself. All right, so that's shear stress and shear strain. Okay, shear modulus is another very important quantity. And of course, you have these new symbols that you have to get used to. So let's move on. This I'm just going to briefly mention. Okay, if you recall it from the very first lecture, I said something along the lines of when you have like a long structure, like some kind of a rod, right? That's in tension or compression. Let's say I'm putting this rod in tension by pulling at a point. Even if I apply this force at a single point, by the time I get far enough away from that point, that force is evenly distributed across the cross-sectional area. So even though when I say sigma is equal to P over A, it kind of assumes that this is an average value. It actually is the value that applies to the whole cross-section. Even if I pick like a little part of this cross-section, the stress at that little point is still going to be P over A because the force P is evenly distributed over that cross-section. Okay. Now, if I were to put a rigid plate, right, and then apply that force P right on that plate, then the force is evenly distributed right from the start. Okay, it's evenly distributed at every single cross-section. But if I apply P as a point force right onto the structure itself, like I showed earlier, then St. Venant's principle says I just need to get a little bit away from the point of application of that force, and that force will be evenly distributed. And just another quick note, right? When you apply a shear stress, remember what we said. This is not the case. St. Venant's principle does not apply to the case of shear. Okay, it only applies to axial loads or normal loads. Okay, so that's all I wanted to say about that. The last topic, okay, in this chapter are what we refer to as stress concentrations. So this is a natural phenomenon that, again, people didn't really know about until they started noticing things that were not as expected. Okay. So let's go ahead and draw something here. If I have a plate that I'm going to pull in tension, okay, then, and I know the dimensions of this plate, and I know what material it's made out of, I'm going to apply P, right? This has some area A. Then I know that the largest force P I could apply, P max, okay, I could find by basically saying the largest stress I could have, the largest stress I could apply until before this starts to break, right, is sigma ultimate. Then I just set that equal to my P max and dividing it by my area. Then I solve for P max, right? And that's fine. That works perfectly, right? People have tested this over and over, and it always works. What happened next was people started looking at situations where they drilled a hole through this plate. Now I'm going to drill a hole through it. So it's got this hole. Okay? And they again try to make this prediction of how large of a force P they could apply. And based on this same analysis, okay, you still use sigma ultimate as P over A, but now you don't use the area of the plate away from the hole. Because if you think about this, right, this force P is the same. If you make a cut anywhere, what is the internal force everywhere you make that cut? It's P. So P never changes. Okay, what does change is your area. So for a given P, what is going to give you the largest stress? It is going to be where your area is smallest. Okay, so where is your area smallest? Is right at the center of that hole. Okay, let me see if I can draw that a little better. Right at the center of that hole, if I were to make a cut, okay, the area is this plus this, as opposed to the whole rectangle, the whole solid rectangle. Okay, so this area is smaller than that area. If I'm applying the same force P, right, then this is going to give me the larger stress. Another way of looking at this is I know I could only apply up to sigma ultimate. If I could only apply up to sigma ultimate, then sigma ultimate is equal to P max divided by area. Okay, so sigma ultimate is a constant. How do I find what the largest force I could apply is? If I use this area, the solid area, right, I get a large value. I multiply that by sigma ultimate to get P max. That gives me a large P max. But if I use this smaller area, multiplied by sigma ultimate, I get a smaller P max. Which P max do I choose, the smaller or the larger? I have to choose the smaller, right? I am limited by my weakest, right? Meaning the stress here reaches the ultimate much faster than the stress here. So that's fine, right? People made that determination. They went through that reasoning and they said, okay, I'm going to take this as my area, and then I just multiply that area by my sigma ultimate, and that should be the largest force that I could apply to this plate. Guess what? When people went and applied that value of P max to the plate, that plate failed well before they were able to get to that force. It was failing much sooner than predicted. Okay. So why is that? The reason behind that is what we refer to as a stress concentration. Okay, so we were talking about how force becomes evenly distributed as you get far away from where your force is applied. Well, once you cut a hole into your plate, once you cut a hole here, right? If you apply a point force, like far enough away from that point force, that force is evenly distributed over the cross-sectional area. But once you get to the hole, that distribution gets pretty messed up again. right? In fact, if you can measure the force distribution, and now there are ways of doing so, if you were able to measure that force distribution, you would see something like this. Okay, this is for a hole. See this bottom left figure here? Okay, what this is showing you is that when you apply that force P, the force P right at the middle of that hole, okay, that force is largest, is distributed so that it's large right at the right where it touches the hole, and then it decreases towards the edge of that hole. So what that means is, if you're looking in terms of stresses, the average stress at the hole here is P over A, but that P over A is not constant. It's not consistent across the area. It's actually largest right at the tip of that hole, and it's smallest at the edge of the plate. So what that means is this sigma max is larger than that average P over A. Okay, so guess where the plates were failing. If you kept pulling on this plate until it failed, where would it fail? It would fail where the stress is largest, right? That means the stress at the edge of this hole reached the ultimate value before any place else. So it always started cracking right at the edge of that hole. And that hole is what we call a stress concentration. Okay. You have something very similar happen when you have a wide plate, right, with D that transitions to a narrow plate with lowercase d. Okay, this case here. The worst thing you could possibly do is to just have a sharp corner here. Okay. So to prevent that, what people do is they round it off. This is what we call a fillet. Okay. But even with the fillet, people found that the largest force they could apply is a lot less than what they predicted based on P over A. Right? So based on P over A, you would say, well, I just take my sigma ultimate and I multiply by the area of the smaller section, right? And that'll tell me how much force I could apply. However, you could actually apply a force that's much smaller than that. And the reason, again, is the stress concentrations. If you look at how the force is distributed, right where the transition starts to happen, the largest stresses are right at the transition. Okay, then it decreases towards the middle. Okay, so what that means, again, is stresses right at that point, right at these 2 points, reach the ultimate value faster than at any other location. So how do we deal with these stress concentrations? Okay. Again, there's no theory that is going to help you with this, so people had to perform a lot of experiments and collect a lot of experimental data. And what they end up with, what people have created, and you can find these in a lot of engineering handbooks, okay, is you look up what is called a stress concentration factor. And the stress concentration factor is a number that's greater than 1, okay? And what it is it tells you the largest stress that actually happens, right? The stress that happens at these stress concentration areas, that stress, right? And this stress, and that's just, it's the ratio of those maximum stresses compared to the average stress that you would calculate based on P over A. Okay, so that increases, a stress concentration factor basically increases the largest amount of stress that you actually have. And the symbol we use for stress concentration factor is capital K. Okay, and it's sigma max divided by sigma average, where your sigma average, again, is your P over A, right? Where you take the area of the minimum of the smallest cross section, P over your A minimum, okay? And the way this works is you go to these plots that you can find in your textbooks or in your engineering handbooks, And these plots will tell you what your stress concentration factor is. Okay, so for instance, right, you take a look at this plate with a hole in it. You need to know what the original width of the plate is, and then you need to know what the radius is, and then what the distance. The distance small d is basically your big width d minus the radius of the hole. Okay, so you need all those values, and then you look up your ratio of your radius of the hole divided by that small value d, lowercase d, right? And then you go up to this plot, and you just go across and determine what your stress concentration factor is. Of course, sometimes you have to interpolate. Right? Once you look up what your stress concentration factor is, now you could go ahead and actually determine what force you could apply. So let me give you an example. Let's say you have a plate with a thickness of 0.1 inch, okay, and then the original width is maybe 2 inches, and you've got a hole here that's 1 inch, 1 inch diameter. Okay, and you're going to make this out of steel, okay, which has, and let's say it's a sigma ultimate is, I'm not sure what it would be. Let's say, I'm going to make something up here, right? Grab something out of thin air. Let's say it's 20 times 10 to the third psi. Okay, something like that. And I want to know what the largest force I could apply is. And let's say you go to that table, right, and you found that K is 2. Find P max. What is the largest force you could pull on this plate with so that it doesn't break? Right? Whoops, I didn't want that. Okay, so how do you do this? Well, let me create some room here for myself. Okay, find P max. All right, so based on our definition, K is equal to sigma max over sigma average. Okay, what is sigma max? Sigma max is the absolute largest stress that you're going to allow in this plate, right? Which in our case, we're going to go right up to the ultimate, okay? We're going to go basically to the breaking point. So 2 is equal to 20 times 10 to the third psi, okay, over sigma average. What is the sigma average? The sigma average is the average stress at the weakest point. That's right there at the hole. Right? So sigma average is going to be equal to whatever force P I'm going to apply is over the area at that point. What is the area at that point? It's thickness, 0.1, right, times that distance and that distance. That's 2 inches minus 1 inch. That's 1 inch. Okay? Notice that the only unknown there is P max, right? You're going to solve for P max, and that would be the largest force you could apply. Okay, can everybody see that? Now, without a stress concentration factor, right, how would you solve for P max? You just say 20 times 10 to the third psi is equal to your P max over that area. Okay? So what is the effect of a stress concentration factor? If you think about this, if you bring that over and divide by 2 on both sides, the effect of this stress concentration factor is to reduce your ultimate stress, or the largest stress you could apply, by half, right? Normally, you could go all the way up to 20 times 10 to the third psi. With a stress concentration factor of 2, you can now only go up to 10 times 10 to the third psi. Okay? So that's how stress concentration factors work. And in the case of the 2 bars, right, a large bar transitioning to a small bar, it's a little more complicated, right? You might now have to interpolate between the different curves, but basically you first find which curve you're going to be using, okay? And then you have to find your value of small r divided by small d, and then you go across to find your k value. And then the rest of it works pretty much the same way. On an exam, okay, if I were to test you on stress concentration factors, I wouldn't give you this chart, right? Because if I gave you this chart and I have you determine your k value, there's some subjectivity, and you're all going to come up with slightly different k values. So I would just give you a problem probably similar to the one we just did, meaning I would tell you what the k value is, okay? And then based on that, you go ahead and find the largest force that you could apply. All right, so there's an example here. You could take a look at it. It's similar to the one we just did, okay, except it's in SI units. And then the rest of this these slides, okay, just ignore. This is the section on plastic deformations, which we're not going to get into. Okay, plastic deformations, as I said, that's more of an advanced thing. And usually in regular mechanics and materials, we don't get into that. Okay, we're going to stay within the linear elastic region. So with that, we have come to the end of chapter 2. Okay, this is the end of this lecture. I know it's rather long. If you combine part 1 and part 2, it's rather long. The rest of the lectures are not going to be quite this long. But chapter 2 is probably one of the longer chapters in the book, because it contains so much fundamental material. This is material we have to get out of the way before we could really move on. All right, so with that, let me sign off on this lecture. Okay, and until next time, feel free to email me with any questions, any comments. Okay, and I'll try to get back to you as soon as I can. There's probably going to be one more week of these video lectures, and then I will be back in the States. Okay, look for an announcement. But I am hoping to basically see you all in just a couple of weeks. All right, so take care and look for my next video sometime soon.